Right now, at this very moment, something massive is tearing through our solar system at a speed that defies comprehension. 219,000 kilometers per hour. Let that sink in for a moment. While you're sitting there, watching this video, breathing normally, living your everyday life, an object weighing more than 33 billion tons is screaming through space faster than anything we've ever seen before. And here's what will make your blood run cold. We have absolutely no idea what it really is. Welcome to the story of 3IATLAS, the interstellar visitor that has NASA scientists working around the clock, that has triggered planetary defense protocols, that has Harvard astrophysicists questioning everything we thought we knew about comets, and that has even caught the attention of Kim Kardashian and Elon Musk. This isn't science fiction. This isn't a movie plot. This is happening right now. And what you're about to discover will fundamentally change how we see our place in the universe. In this video, you're going to learn about an object that shouldn't exist according to our understanding of physics. You'll discover why it changed colors multiple times, why it accelerated when it shouldn't have, why it carries metallic compositions found only in industrial manufacturing, and why one of the world's leading scientists believes it might not be natural at all. You'll find out where it came from, where it's going, and most importantly, whether we should be afraid. Because the uncomfortable truth that NASA doesn't want to emphasize is this: if 3IATLAS were on a collision course with Earth, there would be absolutely nothing we could do to stop it. But before we dive into the shocking details, before we explore the bizarre anomalies that have scientists scratching their heads, and before we examine the possibility that this could be something far more extraordinary than a simple comet, you need to understand one critical fact. What's happening right now has only happened twice before in all of recorded human history. Twice. In thousands of years of looking up at the stars, we've only detected 3 confirmed visitors from another solar system. And this third one, 3IATLAS, is unlike anything we've ever encountered. So buckle up, because what you're about to hear sounds like it came straight from a science fiction thriller, but every single word is based on actual observations, real scientific data, and ongoing investigations by space agencies around the world. The universe just sent us a message, and we're still trying to figure out what it means. It started on July 1st, 2025, in the remote Chilean desert, where a sophisticated telescope system designed to protect Earth from killer asteroids picked up something unusual. The ATLAS Survey Telescope, which stands for Asteroid Terrestrial Impact Last Alert System, detected a faint object moving through space at an absolutely blistering pace. At first, nobody knew what they were looking at. Was it an asteroid? A comet? Something else entirely? The astronomers immediately reported their observations to the Minor Planet Center, setting off a chain reaction that would soon have telescopes all around the world turning their gaze toward this mysterious visitor. Within hours, scientists began analyzing archived images from other telescopes, and they made a stunning discovery. This object had actually been photographed before, but nobody had noticed it. Pre-discovery observations extended back to June 14, 2025, showing that this thing had been silently cruising through our cosmic neighborhood for weeks without anyone realizing what it was. The object had passed in front of the galactic center's dense star fields, making it incredibly difficult to spot among the countless stars in the background. It was hiding in plain sight. But as more telescopes locked onto the target and more data poured in, the reality of what they were seeing began to crystallize, and it sent shockwaves through the astronomical community. The object wasn't just moving fast, it was moving at over 220,000 kilometers per hour, or if you prefer, about 61 kilometers every single second. To put that in perspective, that's fast enough to travel from New York to Los Angeles in less than 20 seconds. It's fast enough to circle the entire Earth in just over 3 minutes. And most importantly, it was moving way too fast to be captured by the sun's gravity. The trajectory calculations confirmed what seemed impossible. This wasn't an object from our solar system. This was an interstellar visitor, something that originated in another star system, perhaps hundreds or even thousands of light years away, that had wandered into our cosmic backyard completely by chance. The astronomers designated it 3IATLAS, where the 3I stands for the third confirmed interstellar object ever detected, and Atlas refers to the telescope system that discovered it. It also received the official comet designation C2025N1. Only 2 other interstellar objects had ever been confirmed before this moment. The first was the infamous Oumuamua, discovered in 2017, which caused a sensation because of its bizarre cigar-like shape and unusual tumbling motion. Harvard astronomer Avi Loeb famously suggested it might be an alien light sail, a claim that sparked intense debate and controversy. The second was 2I Borisov, discovered in 2019, which looked and behaved much more like a normal comet, reassuring scientists that maybe the interstellar visitors weren't so strange after all. But then came 3IATLAS, and it would make both of those previous visitors look ordinary by comparison. As observations continued throughout July, something became clear that would fundamentally change how scientists viewed this object. It wasn't just a rock, it was active. Telescopes detected a bright cloud of gas and dust surrounding the object, what astronomers call a coma, which is the signature feature of a comet. But this wasn't just any coma. The NASA Hubble Space Telescope captured stunning images on July 21, 2025, showing a teardrop-shaped cocoon of material streaming away from the object's nucleus. The images revealed that 3IATLAS had an icy core that was heating up and releasing gases as it approached the sun, creating that characteristic glowing halo around it. Here's where things get interesting. And by interesting, I mean absolutely terrifying in terms of scale. Scientists analyzing the brightness and behavior of 3IATLAS began calculating its size, and what they discovered should make anyone pay attention. The nucleus of this interstellar comet, the solid icy core at its center, was estimated to be at least 440 meters across, but could be as large as 5.6 kilometers in diameter. That's between roughly 1,500 feet and 3.5 miles wide. To give you a sense of scale, that's larger than Mount Everest is tall, and it's heading through our solar system at over 200,000 kilometers per hour. But size was only part of the story. When Harvard astrophysicist Avi Loeb examined detailed observations from the James Webb Space Telescope in August, he calculated something that left him stunned. Based on the rate at which material was being ejected from the comet's surface and the speed of that outflow, he determined that 3IATLAS likely weighs more than 33 billion tons. 33 billion. That's more than 6 million African elephants, more than 30,000 Empire State Buildings, more than 300 fully loaded aircraft carriers. This thing is absolutely massive. And here's what makes it even more remarkable. 3IATLAS is about 1 million times more massive than Oumuamua and roughly 1,000 times more massive than 2I Borisov, while moving faster than both of them. The probability of detecting an interstellar object with this specific combination of size and speed is less than 0.1%. In other words, this shouldn't be happening. This is a statistical outlier, an anomaly that begs for explanation. The coma surrounding 3IATLAS was measured by NASA's SPHERE-X mission and found to be approximately 26,400 kilometers across on average. That's almost twice the diameter of planet Earth. Imagine a cloud of gas and dust bigger than our entire world streaming off a chunk of ice and rock from another solar system. The sheer scale of what we're talking about here is difficult to comprehend. But scale isn't even the weirdest part of the story, not by a long shot. Because as scientists continued their observations throughout the summer and into the fall of 2025, 3IATLAS began doing things that comets simply aren't supposed to do. And that's when the real question started. First, there was the matter of its trajectory. When astronomers calculated the orbital path of 3IATLAS, they discovered something that gave them pause. The comet's trajectory was aligned to within just 5 degrees of the ecliptic plane, which is the flat, disk-like region where all the planets in our solar system orbit around the Sun. Now, space is three-dimensional. An object coming from interstellar space could approach from literally any direction, any angle. The probability of an interstellar visitor just happening to align so closely with the plane where all our planets orbit is about 0.2%. Once again, 3IATLAS was defying the odds. But there's more. Avi Loeb and his team calculated something even stranger about the comet's arrival time. The trajectory of 3IATLAS was perfectly timed to bring it within tens of millions of kilometers from Mars, Venus, and Jupiter, while simultaneously being completely unobservable from Earth during its closest approach to the Sun. The likelihood of this precise timing happening by chance? 0.005%. That's 5 in 100,000. These aren't just unlikely coincidences anymore. These are the kinds of statistical anomalies that make scientists very uncomfortable. Then there was the anti-tail. In July and August of 2025, as 3IATLAS was approaching the inner solar system, astronomers observed something bizarre. The comet displayed what appeared to be a jet of material pointing toward the Sun, creating what's called an anti-tail, or sunward jet. Now, normal comets develop tails that point away from the Sun because solar radiation and the solar wind push the gas and dust backward. It's basic physics. But 3IATLAS seemed to be spraying material forward, ahead of itself, in the direction it was traveling. This wasn't an optical illusion caused by viewing geometry, which sometimes happens with comets. This was actual material being ejected forward, which is extremely unusual. Avi Loeb proposed a fascinating explanation for this forward-facing plume. He suggested that the large dust particles being ejected ahead of 3IATLAS, particles too big to be pushed back by solar radiation pressure, could be creating a buffer zone in front of the comet. And why would a comet need a buffer zone? Well, 3IATLAS was traveling at over 60 kilometers per second through the asteroid belt, a region filled with about 1 trillion rocks larger than 20 meters. At that velocity, even a collision with a relatively small asteroid could release catastrophic amounts of energy. Loeb calculated that if 3IATLAS collided with just a 20-meter asteroid, it would release energy equivalent to 20 megatons of TNT, roughly 1,000 Hiroshima atomic bombs. A protective shield of particles that could detect and warn of incoming obstacles a few minutes in advance might make sense if you were trying to protect something valuable during an interstellar journey. The composition of 3IATLAS added another layer of mystery. When scientists analyzed the light spectrum coming from the comet's coma, they detected carbon dioxide, water, carbon monoxide, carbonyl sulfide, and water ice, all relatively normal for a comet. But they also found something extraordinary, an abundance of nickel that far exceeded the iron content, and traces of nickel tetracarbonyl, a compound rarely found in nature but commonly produced in industrial processes. The ratio of nickel to cyanide in 3IATLAS was orders of magnitude larger than that of any known comet, including the previous interstellar visitor 2I Borisov. This is the kind of metallic composition you'd expect from industrially produced nickel alloys, not from a natural chunk of ice and rock that's been drifting through space for billions of years. And then we come to the color changes, which might be the strangest phenomenon of all. When 3IATLAS was first observed in the summer of 2025, it displayed a reddish hue, similar to what's seen in many solar system comets and asteroids. This reddish color is typically caused by irradiated organic compounds called tholins in the comet's coma. Nothing unusual about that. But then, as it approached closer to the Sun, something bizarre happened. The comet began to change color multiple times. Observations revealed that at different points in its journey, 3IATLAS shifted from red to what appeared to be a deep blue coloration, something highly atypical for comets, which usually redden as sunlight scatters through the dust around them. The blue color was so unexpected that it prompted Avi Loeb to write that, for a natural comet, this blue color is very surprising. He noted that the blue hue could potentially be explained by ionized carbon monoxide in a natural comet, but he also raised the eyebrow-raising possibility that it could be a signature of something else entirely. In the days before the comet reached its closest point to the Sun, astronomers recorded a sudden and dramatic brightening. The object increased in luminosity by a factor of about 5 in certain wavelengths of light, suggesting that massive amounts of material were being ejected from its surface. This kind of outburst can happen when frozen gases suddenly vaporize under intense solar heating, but the magnitude and timing of the brightening were unusual enough to raise questions. The comet reached perihelion, its closest approach to the Sun, on October 29, 2025, just 2 days before Halloween. At this point, it was about 203 million kilometers from the Sun, or roughly 1.4 times the distance from Earth to the Sun, passing just inside the orbit of Mars. For several weeks, 3IATLAS was positioned directly behind the Sun from Earth's perspective, which made it impossible for ground-based telescopes to observe it. This was a critical period because this was when the most important test of the comet's nature would occur. You see, as any object approaches the Sun, it experiences increasing gravitational pull which accelerates it toward our star. But for 3IATLAS, something else happened that sent shockwaves through the scientific community. NASA's Jet Propulsion Laboratory reported detecting non-gravitational acceleration. The comet was moving faster than gravity alone could explain. Non-gravitational acceleration in comets isn't completely unknown. When comets get close to the Sun, the heat vaporizes frozen gases on their surface, and these jets of gas can provide a small rocket-like thrust that changes the comet's trajectory slightly. It's called outgassing, and it's a well-understood phenomenon. But the acceleration detected in 3IATLAS was unusually strong, much more powerful than what's typically seen in normal comets. The measurement stood at a confidence level of 3.7 standard deviations, meaning there was less than 0.02% chance this was just random noise in the data. This was real. Avi Loeb calculated that based on the level of non-gravitational acceleration detected, 3IATLAS should have lost more than 13% of its total mass during its perihelion passage. For a comet weighing more than 33 billion tons, that means it should have ejected at least 4 billion tons of material. 4 billion tons! The momentum carried away by that much gas and dust should have created an absolutely massive cometary tail, a spectacular plume of debris stretching millions of kilometers behind the comet, pushed away from the Sun by radiation pressure and the solar wind. But here's the problem. When 3IATLAS emerged from behind the Sun in early November and telescopes were finally able to observe it again, there was no massive tail. Images captured on November 5, 2025 by the RN Navas Observatory in Spain and the Virtual Telescope Project showed a compact source of light with a diffuse coma, but no clear cometary tail pointing away from the Sun. The morphology looked remarkably similar to how the comet appeared back in July, before perihelion, as if it hadn't just undergone a massive outgassing event. Avi Loeb noted this in his analysis, expressing surprise and pointing out that a typical comet losing that much mass should have produced a dramatic tail. So where did all that material go? Why wasn't there visible evidence of the massive mass loss that the acceleration data suggested? For comparison, another comet in our solar system, named Lemon, was photographed around the same time by the same telescopes, and it showed a clear, prominent cometary tail pointing away from the Sun exactly as expected. But 3I-ATLAS looked like a fuzzy ball with no obvious tail structure. This discrepancy between what the non-gravitational acceleration implied should happen and what was actually observed added yet another anomaly to the growing list of strange behaviors. Now, let's talk about the elephant in the room, or rather, the spaceship in the room. Harvard University astronomer Avi Loeb, one of the most prominent astrophysicists in the world, has been asking questions that make many of his colleagues uncomfortable. In a series of essays and scientific papers published throughout the summer and fall of 2025, Loeb has raised the possibility, however remote, that 3I-ATLAS might not be entirely natural. He's not claiming it's definitely alien technology. He's simply arguing that given the number and nature of the anomalies, scientists have a responsibility to seriously consider all possibilities, including the unconventional ones. Loeb developed something called the Loeb scale, a metric for assessing the technological threat level of interstellar objects on a scale from 0 to 10. He ranks 3I-ATLAS at a 4, not alarming but worthy of close scrutiny. He emphasizes that the simplest hypothesis is that 3I-ATLAS is a natural comet, but he warns against dismissing unconventional possibilities too quickly. As he told Fox News, the fundamental question is whether 3I-ATLAS might be what he calls a Trojan horse, with the external appearance of a natural comet, but potentially carrying something unexpected in its interior. In a white paper submitted to the United Nations in September 2025, Loeb and his collaborators advocated for coordinating global scientific research to maximize observational coverage and ensure optimal monitoring of interstellar objects like 3I-ATLAS, which could potentially pose a threat to humanity if they happen to carry alien technology, however unlikely that may be. The paper argued that black swan events with small probabilities must be considered seriously if their implications for the future of humanity are large. It's a reasonable point. If there's even a 1% chance, or 0.1% chance, that an interstellar object could represent a technological artifact from another civilization, shouldn't we investigate thoroughly rather than assuming it's natural? NASA, for its part, has been quite firm in its assessment. Acting Administrator Sean Duffy, responding to a question from Kim Kardashian on social media, stated unequivocally that 3I-ATLAS is the third interstellar comet to pass through our solar system, with no aliens and no threat to life on Earth. Tom Statler, NASA's lead scientist for solar system small bodies, told reporters that the object looks like a comet, does comet things, and very strongly resembles in just about every way the comets that scientists already know. The official NASA position is that this is a natural phenomenon and there's nothing to worry about. But here's what makes this whole situation so fascinating and frankly unsettling. Both positions can be simultaneously true based on the available evidence. Yes, 3I-ATLAS displays cometary activity. Yes, it has an icy nucleus and a coma. Yes, outgassing can explain the non-gravitational acceleration. But yes, it also has a statistically improbable trajectory. Yes, it has unusual metallic composition. Yes, it changed colors in unexpected ways, and yes, it lacks the massive tail that should have formed. These anomalies don't prove anything extraordinary, but they do raise legitimate scientific questions that deserve investigation. What makes the current moment particularly intriguing is that we're still in the middle of the observation period. This isn't ancient history, this is happening now. 3I-ATLAS is still cruising through our solar system, and every day brings new data and potentially new surprises. The International Asteroid Warning Network, which is part of the United Nations Planetary Defense Framework, announced in October that it was initiating a special campaign to monitor 3IATLAS from late November 2025 through January 2026. The stated purpose is to improve methods for tracking comets, but the timing is certainly interesting given all the unusual features this object has displayed. NASA triggered its Planetary Defense Protocol in response to the unusual behavior observed in 3IATLAS, mobilizing the International Asteroid Alert Network to coordinate data sharing and simulations. This doesn't mean NASA thinks there's a threat. Planetary defense protocols are standard procedure for unusual space objects, especially ones that exhibit unexpected behaviors. But the fact that these protocols were activated demonstrates that the scientific community is taking this seriously. Multiple space agencies around the world have turned their instruments toward 3IATLAS. NASA's Hubble Space Telescope, James Webb Space Telescope, TESS Satellite, Swift Observatory, and numerous Mars missions, including the Perseverance rover, Mars Reconnaissance Orbiter, and Curiosity rover, have all gathered observations. The ESA pointed Mars Express, the ExoMars Trace Gas Orbiter, and even the Jupiter Icy Moons Explorer spacecraft called JUICE toward the comet to make observations from different vantage points across the solar system. The goal is to get as complete a picture as possible of this object's nature, composition, and behavior. Some of the most anticipated observations came from the Mars missions. On October 3, 2025, 3IATLAS passed within approximately 30 million kilometers from Mars, and ESA's Mars orbiters captured images with multiple instruments. There has been significant interest and some controversy surrounding one particular set of observations. Harvard's Avi Loeb publicly called for NASA to release images taken by the high-rise, high-resolution camera aboard the Mars Reconnaissance Orbiter, suggesting during an appearance on Joe Rogan's podcast that NASA might be withholding evidence. NASA has stated that it intends to release findings and observations once they're properly analyzed, and that no evidence is being suppressed. A government source confirmed that NASA officials are tracking the comet and plan to discuss 3IATLAS with members of Congress, indicating that there's significant political interest in this object at the highest levels. So where is 3IATLAS now, and where is it headed? As of early November 2025, the comet has passed perihelion and is now moving away from the Sun, heading back out toward the outer solar system and eventually into interstellar space again. It's following a hyperbolic trajectory, meaning it will never return. This is a one-time visit. After it leaves, we'll never see it again, at least not in our lifetimes or our children's lifetimes, or probably for thousands of generations. The comet already passed close to Venus on November 3rd, coming within 97 million kilometers of that planet. On December 19, 2025, just 6 days before Christmas, 3IATLAS will make its closest approach to Earth, though at a very safe distance of about 170 million miles or 270 million kilometers. That's roughly 1.8 astronomical units, or nearly twice the distance from Earth to the Sun. There is absolutely zero chance of impact, none. The comet's trajectory is well understood, and it's on a path that keeps it far away from our planet. But then things get interesting again. On March 16, 2026, 3IATLAS will arrive at its closest distance from Jupiter, passing within about 54 million kilometers of the gas giant. NASA's Juno spacecraft, which is currently orbiting Jupiter, will have an opportunity to observe the comet from relatively close range, and could potentially use its radio antenna to check for any unusual radio emissions. In a fascinating analysis, Avi Loeb and his colleagues calculated that if Juno had its initial fuel supply, it theoretically could have been maneuvered to intercept 3IATLAS at this point. Congresswoman Anna Paulina Luna even sent a letter to NASA suggesting this possibility, though the European Space Agency has stated that sending a spacecraft to study 3I-ATLAS is impractical due to its high speed and the limited time it will remain in our solar system. After the Jupiter encounter, 3I-ATLAS will speed away into the darkness beyond, carrying whatever secrets it holds back into the vast emptiness between the stars. Within a few years, it will be too faint and too distant for even our most powerful telescopes to detect, and it will disappear from human knowledge forever, becoming just another wanderer in the cosmic night, traveling for perhaps millions or billions of years before it possibly encounters another star system. Now let's address the big question everyone wants answered. Should we be worried? Is 3I-ATLAS dangerous? The unequivocal answer from every space agency and every mainstream scientist is no. NASA has stated clearly and repeatedly that 3I-ATLAS poses no threat to Earth whatsoever. The closest it will come is 170 million miles away, which in cosmic terms is nowhere near close enough to cause any concern. There is zero chance of impact, none. The comet's trajectory is well understood, and it's on a path that keeps it far away from our planet. But here's the uncomfortable reality that Elon Musk pointed out during his discussion of 3I-ATLAS on Joe Rogan's podcast. While this particular object poses no threat right now, its potential to cause catastrophic damage if it were on a collision course cannot be ignored. An object weighing 33 billion tons hitting Earth at over 200,000 kilometers per hour would release energy equivalent to millions of nuclear weapons. It would be an extinction-level event, the kind of impact that could wipe out most life on the planet. The dinosaurs were killed by an asteroid that was probably much smaller than 3I-ATLAS. If an interstellar object this size ever did come toward Earth, we would have no way to stop it. Our current technology couldn't deflect or destroy something this massive, moving this fast. We would be completely helpless. This is why planetary defense is taken so seriously by space agencies around the world. It's why systems like ATLAS exist to detect potentially dangerous objects as early as possible. It's why NASA and other agencies run simulations and develop contingency plans, not because there's an imminent threat, but because the consequences of being unprepared would be so catastrophic that even a very low probability event demands attention and resources. The discovery of 3I-ATLAS has profound implications beyond just this one object. For one thing, it tells us that interstellar visitors are probably more common than we thought. Before Oumuamua was discovered in 2017, we had detected exactly 0 interstellar objects in all of human history. Then we found 2 more in just 8 years. Statistical models based on these detections suggest that at any given moment, there might be thousands of interstellar objects passing through our solar system, most of them too small or too faint for us to detect with current technology. The NSF-DOE Rubin Observatory in Chile, which is expected to begin operation soon, is projected to detect dozens of interstellar objects in the next decade. With each new discovery, we'll learn more about what's drifting through the space between the stars, what kinds of materials exist in other solar systems, and potentially even find clues about the formation and evolution of planetary systems throughout the galaxy. Every interstellar visitor is like a free sample from another part of the universe, carrying information about conditions and processes happening light years away. There's even a deeper philosophical implication here. Some scientists have suggested that interstellar objects like 3I-ATLAS could play a crucial role in spreading the building blocks of life throughout the galaxy. The theory of panspermia proposes that life, or at least the complex organic molecules necessary for life, might be distributed between star systems by comets and asteroids that travel through interstellar space. 3I-ATLAS contains carbon dioxide, water, organic compounds, and other materials relevant to biology. If it carried these materials from another star system and deposited some of them here through outgassing or perhaps through micro-collisions with dust in our solar system, it could theoretically contribute to the molecular inventory available for life. The same process happening over billions of years across countless star systems could help explain why life might arise in multiple locations rather than being a unique accident that happened only on Earth. From a search for extraterrestrial intelligence perspective, 3IATLAS is also fascinating. For decades, SETI researchers have focused primarily on detecting radio signals or optical transmissions from distant civilizations. But what if advanced civilizations also use interstellar objects as probes or communication devices? What if they send instrumented spacecraft disguised as or incorporated into natural comets and asteroids? After all, if you wanted to study another star system without being obvious about it, camouflaging your probe as a natural object would be an effective strategy. Avi Loeb's Galileo project, based at Harvard's Center for Astrophysics, has expanded its research efforts specifically to analyze data on 3IATLAS and future interstellar visitors. The project is hiring new postdoctoral researchers and developing new analytical tools. Avi has even proposed an alert system of solar-orbiting telescopes and interceptor spacecraft that could be deployed to study future interstellar objects before they leave our solar system. The idea would be to position a network of spacecraft in orbits around the Sun equipped with sensors and propulsion systems capable of quickly rendezvousing with newly detected interstellar visitors. When something interesting shows up, you send an interceptor to get close-up observations, take samples if possible, and maybe even answer definitively whether these objects are natural or artificial. It's worth noting that NASA and other space agencies are already thinking along these same lines, though perhaps not with the same emphasis on looking for technological signatures. The European Space Agency's Comet Interceptor mission, currently in development, is designed to visit a comet coming directly from the outer reaches of the solar system, carrying material untouched since the dawn of time. ESA has acknowledged that while it's very unlikely given their rarity, Comet Interceptor could potentially be redirected to visit an interstellar comet if one appears at the right time and place. Having spacecraft ready and waiting to intercept these rare visitors would be invaluable for science. The age of 3IATLAS is another mind-blowing aspect of this story. Based on analysis of its composition and the effects of cosmic ray bombardment on its surface, some estimates suggest this object could be more than 7 billion years old, possibly as much as 10 billion years old. That would make it twice as old as Earth, older than our Sun, one of the oldest physical objects ever directly observed by humanity. Think about that for a moment. This chunk of ice and rock has been wandering through the Milky Way galaxy for billions of years, since a time when our solar system didn't even exist. It witnessed the birth and death of countless stars. It drifted through regions of space we can barely imagine, through nebula and dust clouds, past star systems we'll never see. And purely by chance, by an incredible cosmic coincidence, its path happened to intersect with our solar system at exactly the moment in history when humanity had developed the technology to detect it and study it. Where did 3IATLAS come from originally? We don't know. We can't trace its trajectory backward with enough precision to identify a specific star system of origin. It could have been ejected from a planetary system during the chaotic early stages of planet formation, when gravitational interactions between forming planets often fling debris into interstellar space. It could have been part of a star system that was destroyed when its parent star went supernova or merged with another star. It could have been wandering between the stars for so long that its birthplace is now completely unrecognizable, transformed by stellar evolution or swallowed by a black hole. We'll probably never know for certain. What we do know is that space is full of these wanderers. For every interstellar object we detect, there are probably millions that pass through unnoticed. Some are too small, some are too far away, some move through parts of the solar system where we don't have good telescope coverage. Some pass by too quickly. Every year, countless chunks of rock and ice from other star systems enter our solar system, travel through it, and leave without anyone ever seeing them. We're just now developing the technology and the survey programs to catch a tiny fraction of them. The 3 interstellar objects we've detected so far, Oumuamua, 2I Borisov, and 3IATLAS, are remarkably different from each other, which suggests that there's probably enormous diversity in these populations. Oumuamua was small, elongated, tumbling oddly, and showed no signs of cometary activity. 2I Borisov looked and acted like a fairly normal comet, with a clear tail and outgassing behavior that matched predictions. 3IATLAS is massive, fast, chemically unusual, and displays behaviors that don't perfectly fit the standard comet model. If these 3 objects are representative of what's out there, then interstellar space contains a wild variety of objects with different origins, compositions, and histories. Some scientists have pointed out that detecting 3 interstellar objects in less than a decade suggests our detection methods are getting much better. But it might also mean these objects are more common than previous models predicted. If interstellar objects regularly pass through star systems, and if they carry organic molecules and volatiles, then the exchange of material between star systems might be an important process in galactic chemistry and possibly even in the distribution of life-related molecules. The universe might be more connected than we realize, with matter constantly flowing between stars, mixing and sharing the products of stellar nucleosynthesis and planetary processes across vast distances. The public reaction to 3IATLAS has been fascinating in its own right. When was the last time an astronomical discovery captured mainstream attention to this degree? When Kim Kardashian tweets asking, "What's the T on 3IATLAS?" with multiple question marks and exclamation points, you know something has broken through into popular consciousness. When Elon Musk discusses it on one of the most popular podcasts in the world, when mainstream news outlets run continuous coverage, when government officials feel compelled to issue reassuring statements, it indicates that this story has resonated with people in a way that most space science doesn't. Part of the appeal is the inherent drama of the situation. An object from another star system, possibly billions of years old, screaming through our cosmic neighborhood at incomprehensible speed, exhibiting bizarre behaviors that puzzle scientists, arriving at a time when we're just barely technologically capable of studying it. It's the stuff of science fiction come to life. But there's also an undercurrent of anxiety, a primal fear that maybe, just maybe, something out there in the darkness could threaten us. NASA's reassurances help, but they also paradoxically feed the speculation. Why does NASA need to reassure us unless there's something to be worried about? Of course, the reality is that NASA is simply doing its job, providing factual information to counter misinformation and unnecessary panic. But in an age of conspiracy theories and distrust of institutions, even straightforward scientific communication gets interpreted through multiple lenses. The involvement of figures like Avi Loeb adds another dimension to the public discourse. Loeb is a highly credentialed scientist with an impressive academic pedigree. Chair of Harvard's Astronomy Department, founding director of a major astrophysics institute, author of hundreds of scientific papers, and recipient of numerous prestigious awards. When someone with those credentials raises unconventional possibilities, it carries weight. But Loeb is also a controversial figure within astronomy. Many of his colleagues criticize what they see as his tendency to jump to exotic explanations before exhausting mundane ones, his eagerness to engage with media and popular audiences, and his willingness to entertain ideas that most scientists consider extremely improbable. The scientific debate about how to interpret unusual observations like those from 3IATLAS goes to the heart of how science should work. On one hand, you have the principle of Occam's razor, which suggests that the simplest explanation that fits the data is usually correct. Comets can be weird. Comets can do unexpected things. Cometary science is complex, and we're constantly discovering new behaviors and phenomena. When you see something unusual about a comet, the default assumption should be that it's a natural process we don't fully understand yet, not that it's artificial. This is the position of most astronomers. On the other hand, science also requires openness to paradigm-shifting discoveries. Every major scientific revolution began with someone taking seriously an idea that seemed ridiculous to their contemporaries. Meteorites falling from the sky? Ridiculous, until it wasn't. Continents drifting across the Earth's surface? Absurd, until it wasn't. Bacteria causing ulcers? Laughable, until it wasn't. The universe expanding? Time slowing down near massive objects? Quantum entanglement? All of these ideas were initially dismissed or ridiculed before evidence forced their acceptance. So, while extraordinary claims require extraordinary evidence, they shouldn't be dismissed out of hand simply because they're extraordinary. Loeb's argument is essentially that we should look. We should take the possibility seriously enough to gather the best possible data and analyze it rigorously. We should design observations and experiments that could potentially distinguish between natural and artificial origins, if such a distinction is even possible. And we should do this not because we expect to find alien technology, but precisely because the implications would be so profound that even a very small probability deserves investigation. As Loeb puts it, if you don't look, you definitely won't find anything. The absence of evidence is not evidence of absence, especially when you haven't really looked. The counter-argument from mainstream astronomy is that resources are limited, and spending time and telescope time chasing extremely unlikely possibilities means not doing other valuable science. If every weird observation gets treated as potential evidence of alien technology, you end up in a state of perpetual distraction, forever chasing phantoms instead of making real progress on understanding the natural universe. Moreover, there's a concern about public perception and credibility. If scientists constantly speculate about aliens, the public might lose faith in scientific judgment and rigor. Better to stick to what the evidence clearly supports and only invoke extraordinary explanations when absolutely forced to by the data. Both perspectives have merit, and the tension between them is actually healthy for science. The conservative approach prevents wild speculation and maintains rigorous standards. The unconventional approach prevents groupthink and ensures that genuinely revolutionary discoveries don't get missed because they don't fit the prevailing paradigm. The key is maintaining intellectual honesty and following the evidence wherever it leads, while also being appropriately skeptical and demanding high standards of proof. In the specific case of 3IATLAS, what would constitute compelling evidence that something unusual was going on? Well, for starters, if the object were emitting radio signals in patterns that couldn't be explained by natural processes, that would be significant. If it changed course in ways that couldn't be explained by outgassing or gravitational interactions, that would be significant. If close-up observations revealed artificial structures or materials that couldn't form naturally, that would be definitive. None of these things have been observed. All the anomalies detected so far, while unusual, can potentially be explained by natural processes, even if we don't fully understand those processes yet. The lack of a prominent cometary tail after perihelion is puzzling, but there are possible natural explanations. Maybe the mass loss occurred in a way that didn't produce large dust particles capable of scattering visible light effectively. Maybe the tail is there but oriented in a way that makes it hard to see from Earth's vantage point. Maybe the composition of 3IATLAS is such that its outgassing produces mostly gas and small particles that are transparent to visible light. Maybe the non-gravitational acceleration detected by JPL was overestimated or came from a brief outburst rather than sustained mass loss. More observations and analysis will hopefully clarify these questions. And that, in a way, is what makes astronomy both frustrating and beautiful. We're looking at the universe through a narrow window, catching glimpses of vast processes and ancient objects, constructing theories and models from fragmentary evidence, always aware that there's infinitely more that we don't see and don't know than what we do. 3IATLAS is a reminder of our cosmic context, a messenger from the depths of space carrying information about places and times utterly alien to human experience. Whether it's just an ordinary interstellar comet or something more unusual, whether the anomalies are real or observational artifacts, whether natural processes can explain everything, or whether we're missing something important, the story of 3IATLAS represents a milestone in human exploration and understanding. We're living in a unique moment in history when we're detecting and studying objects from beyond our solar system for the first time. Our children and grandchildren will grow up in a world where interstellar visitors are routine discoveries, where detecting and characterizing these objects is standard practice, where we have comprehensive databases of hundreds or thousands of them. But right now, today, we're pioneers in this new frontier, and 3IATLAS is only the third such object we've ever studied. The media attention and public interest in 3IATLAS, while sometimes sensationalized, reflects a genuine hunger for cosmic discovery and a recognition that we're part of something larger than ourselves. In an age of political division, economic anxiety, and social turmoil, there's something unifying about looking up at the sky and contemplating objects that transcend all human concerns. 3IATLAS doesn't care about borders or politics or ideologies. It's just a chunk of ice and rock, or possibly something more, moving through space according to the laws of physics, indifferent to our interpretations and speculations. The question of whether we're alone in the universe lurks beneath the surface of discussions about 3IATLAS. If it's natural, it's still fascinating, but it doesn't change our fundamental understanding of our place in the cosmos. If it were somehow artificial, if it carried instrumentation or represented technology from another civilization, that would be the most significant discovery in human history. It would mean that intelligence and technology have arisen elsewhere, that we're not unique, that the galaxy might be populated with minds capable of understanding and manipulating the physical world. The statistical arguments about the improbability of detecting large, fast interstellar objects cut both ways. Yes, detecting something like 3IATLAS is unlikely if interstellar comets are randomly distributed and randomly oriented. But if technological civilizations exist, and if they send probes to explore other star systems, those probes would likely target star systems with planets, particularly those with habitable zones where life might arise. Our solar system would be an obvious target. Such probes might also preferentially arrive in trajectories aligned with the ecliptic plane, because that's where the most interesting stuff is in most solar systems, and they might time their arrivals to pass multiple planets for optimal observational opportunities. In other words, some of the features that make 3IATLAS statistically unusual as a random interstellar object might be exactly what you'd expect if it were a deliberate visitor. Of course, this logic can become circular. If you assume something might be artificial, you can interpret any unusual feature as supporting that assumption. This is why the burden of proof rightly lies with those proposing unconventional explanations. Extraordinary claims require extraordinary evidence. And so far, the evidence for 3IATLAS being anything other than a natural comet is circumstantial at best. Multiple anomalies don't add up to proof of artificiality. They add up to an interesting and puzzling object that doesn't perfectly fit our models, which is actually fairly common in astronomy. The universe regularly produces phenomena that challenge our understanding without being artificial. Nevertheless, the possibility, however remote, keeps nagging at the back of the mind. What if? What if we're being visited by interstellar probes and we're too stuck in our assumptions to recognize them? What if civilizations throughout the galaxy routinely send spacecraft disguised as natural objects to study other star systems without being detected? What if 3IATLAS is silently observing us, even now, recording everything it sees, and will eventually carry that information back to whoever sent it? These are the kinds of questions that make great science fiction, and they're not entirely unreasonable as thought experiments, even if they're wildly unlikely to be true. Any sufficiently advanced civilization would presumably have the capability to send probes to other star systems. If they wanted those probes to go unnoticed, or if they simply wanted them to last for billions of years traveling through the harsh environment of interstellar space, they might encase them in ice and rock, creating objects that would be indistinguishable from natural comets to casual observation. The ice would provide radiation shielding, impact protection, and propellant for trajectory adjustments. A probe could hibernate for millions of years, wake up when it detected a star system, shed some of its protective coating to maneuver, make its observations, and then depart, leaving behind only brief glimpses and puzzling data for any astronomers who happen to notice it. But let's be clear, there is no credible evidence that 3IATLAS is an alien probe. The evidence that exists is entirely consistent with it being a natural interstellar comet, albeit one with some unusual characteristics that we don't fully understand yet. NASA is right to emphasize this. The scientific consensus is right to treat exotic explanations with appropriate skepticism. The burden of proof for claiming something is artificial is enormously high, and that burden has not been met.
The unusual metallic composition, particularly the high nickel content, is interesting but not inexplicable. Different star systems have different metallicities, depending on when and where they formed and what elements were available in the molecular clouds that birthed them. A planetary system that formed in a region of the galaxy rich in certain elements, or that experienced unusual nucleosynthetic processes, could produce objects with atypical compositions compared to what we see in our solar system. The presence of nickel tetracarbonyl is intriguing because it's associated with industrial processes on Earth, but carbonyl complexes can form naturally under the right temperature and pressure conditions, particularly in carbon-rich environments. It's unusual, but not impossible. The color changes from red to blue and back are harder to explain with standard cometary models, but not impossible. Different volatiles vaporizing at different temperatures as the comet approaches and then recedes from the sun could potentially cause color variations. Ionized gases emit light at specific wavelengths that could shift the apparent color. Changes in the dust-to-gas ratio in the coma could affect how sunlight scatters. There are several natural mechanisms that could potentially account for what was observed, even if none of them perfectly matches the specific pattern seen in 3IATLAS. The statistically improbable trajectory and timing are the elements that give even skeptics pause. Yes, unlikely things happen. By definition, something with a 0.005% probability should happen about one time in 20,000. But when you have multiple unlikely things happening together, the compound probability becomes genuinely surprising. It's the difference between flipping a coin and getting heads 5 times in a row, which is unlikely but will happen occasionally, versus flipping a coin and getting heads exactly 5 times in the first 5 flips on exactly the day you predicted it would happen in a room with 5 people whose names all start with the letter H. At some point, stacked coincidences become suspicious. But suspicious doesn't mean artificial. Space is weird. The universe is full of unlikely events because there are so many opportunities for unlikely events to occur. With billions of stars in the galaxy and trillions of comets and asteroids constantly in motion, eventually you're going to see some very strange coincidences purely by chance. The question is whether the coincidences associated with 3IATLAS are strange enough to warrant serious consideration of unconventional explanations, or whether they're within the range of weirdness that natural processes can produce. One thing that would help resolve these questions would be a close-up mission to 3IATLAS. But as mentioned earlier, that's not practically possible with current technology. The comet is moving too fast and is already too far away. By the time we could design, build, launch, and maneuver a spacecraft to intercept it, 3IATLAS would be beyond the orbit of Uranus and rapidly becoming unreachable. The window of opportunity to get a probe to it has basically closed, which is frustrating because detailed imaging and in situ measurements could answer many of the outstanding questions definitively. This limitation highlights a broader challenge in studying interstellar objects. They don't stick around. They're here and gone, passing through our solar system on timescales of months to a few years, and by the time we detect them, analyze their orbits, and mobilize resources to study them, they're already leaving. It's like trying to study a bird in flight when you only notice it after it's already halfway across the sky. You can observe it for a little while, but you can't catch it, you can't examine it up close, and you certainly can't bring it back to a laboratory for detailed analysis. This is why proposals for pre-positioned interceptor spacecraft make sense. If we had a network of small probes already in space, equipped with propulsion systems and scientific instruments ready to quickly fly to newly detected interstellar objects, we could gather much more comprehensive data. The technology to do this exists. It's mostly a question of funding and priorities. Is studying interstellar visitors important enough to justify the cost of maintaining a fleet of ready-to-go probes? NASA and other space agencies are still debating that question. Meanwhile, ground-based and space-based telescopes continue to track 3IATLAS as it moves outward. Every observation adds to our understanding, even if each individual data point raises as many questions as it answers. Astronomers are analyzing the light curves, studying the spectroscopic data, modeling the coma dynamics, and comparing everything to observations of other comets. Over time, patterns will emerge, hypotheses will be tested, and the scientific consensus will converge on the most likely explanation for what we're seeing. But even after all the analysis is complete and papers are published and the scientific community reaches a consensus, 3IATLAS will remain, in some sense, mysterious. We'll never know its complete history. We'll never know exactly which star system it came from or what events led to its ejection into interstellar space. We'll never know what it experienced during its billions of years wandering through the galaxy. We'll never know if it passed through other star systems before reaching ours, or if we were the first. All we have is this brief snapshot, a few months of observations, capturing a tiny slice of an incredibly long journey. What 3IATLAS definitely represents, regardless of its precise nature, is a reminder of how much we still have to learn about the universe. Cometary science is complex and full of surprises. Every comet is unique in some ways, shaped by its formation environment, thermal history, and evolutionary path. When you add the complexity of interstellar comets, which formed in completely different stellar environments, with potentially different chemical compositions and physical conditions, the range of possible behaviors expands enormously. We've now observed exactly 3 interstellar objects total. We've seen 3 examples. Drawing broad conclusions from a sample size of 3 is scientifically problematic. We need dozens or hundreds of detections before we can really say what's typical and what's anomalous for interstellar visitors. The next few months will bring additional observations as 3IATLAS continues its outbound journey past Jupiter. The encounter with Jupiter in March 2026 will be particularly interesting because Jupiter's powerful gravity will alter the comet's trajectory slightly, and observing exactly how that happens will provide information about the comet's mass distribution and structure. NASA's Juno spacecraft might detect changes in Jupiter's magnetic field as the comet passes, though at a distance of 54 million kilometers, any effects would be extremely subtle. After Jupiter, 3I/ATLAS will rapidly fade as it moves into the outer solar system. By late 2026 or early 2027, it will probably be too faint for most telescopes to detect, even large research observatories. It will effectively disappear from human observation, becoming once again just another wanderer in the cosmic darkness, invisible and unknowable. Somewhere around 2028 or 2030, it will cross the orbit of Neptune and officially enter the outer reaches of our solar system. By 2035 or 2040, it will be beyond the Kuiper Belt. By the end of the century, it will be leaving the heliosphere, the bubble of solar wind that surrounds our sun. And then it will be truly back in interstellar space, traveling through the void between stars, continuing a journey that began billions of years ago and might continue for billions more. Will 3I/ATLAS ever encounter another star system? Probably. The galaxy is vast, but so is time. Given enough time, most objects in motion will eventually pass near something. In a few million years, 3I/ATLAS might drift through another planetary system, where perhaps alien astronomers will detect it and wonder about its origins just as we've wondered. They might see the same anomalies we saw and have the same debates we're having. Or maybe they'll have technology capable of capturing it and studying it in detail, definitively determining its nature in ways we couldn't. Or maybe it will pass through that system unnoticed, as it probably passed through countless systems unnoticed before reaching ours. The story of 3I/ATLAS also raises important questions about planetary defense and our preparedness for unexpected threats from space. While this particular object poses no danger, the fact that we only detected it a few months before it reached its closest approach to the inner solar system is sobering. If an object like this were on a collision course with Earth, a few months would be nowhere near enough time to mount an effective defense. We'd be doomed. Simple as that. Current planetary defense strategies rely on detecting potentially hazardous asteroids years or decades in advance, giving time to prepare and execute a deflection mission. But interstellar objects by definition come from outside our solar system and aren't in the catalogs of known near-Earth objects. They appear with little warning, move incredibly fast, and leave quickly. This doesn't mean we're helpless, but it does mean we need better detection systems. Programs like ATLAS and the upcoming Rubin Observatory are steps in the right direction, providing continuous monitoring of the sky to detect fast-moving objects as early as possible. The goal is to push the detection window back from months to years, giving more time to assess threats and develop responses if necessary. It's also why some scientists advocate for space-based telescopes dedicated to planetary defense, which could monitor the entire sky continuously without atmospheric interference or daylight limitations. The international cooperation triggered by 3I/ATLAS is encouraging. Space agencies from multiple countries shared data, coordinated observations, and worked together to understand this object. If a genuine threat ever materialized, that kind of cooperation would be essential. Planetary defense is inherently a global challenge because an asteroid impact anywhere on Earth would have global consequences. It's one of the few issues where national interests align so perfectly that international cooperation becomes not just desirable, but necessary. From an educational perspective, 3I/ATLAS has been valuable for engaging public interest in astronomy and space science. Schools and universities are using it as a teaching opportunity, explaining concepts like orbital mechanics, spectroscopy, cometary physics, and the scientific method. Students are analyzing publicly available data, writing papers, participating in online discussions. The controversy and debate surrounding the comet's unusual features make it a perfect case study in how science works, how scientists evaluate evidence, how they handle uncertainty, and how they navigate between healthy skepticism and openness to new ideas.